Hi, and welcome to a video on Calculus 1 areas and distances. So let's start by talking about four important sums that we're going to need as we develop this idea of a Riemann sum. If I take the sum, and this sigma right here, this funny E, is the summation or sigma notation. And so we're saying we're going to take the sum starting at 1 and ending at n of all c values, so some constant value. So that would be like me having 5 plus 5 plus 5 plus 5 plus 5 n times. That sum would be 5n or Cn. So we do the same thing. Now the term that we are adding is going to be changing. So the sum of all I, when I is going from 1 to n. And what that would look like is 1 plus 2 plus 3 plus 4 plus 5, and I'll just go to 100. Let's say 96, 97, 98, 99, and 100. And so what they've discovered in this summation is that if you take 1 and this 100, you have a sum of 101. And if you take the next two in here, 2 and 99, you also have a sum of 101. 3 and 98, you also have a sum of 101. 4 and 97, and so forth. 596, right? And all of them in between. And so because you're pairing them up in two, if I go from 1 to 100, for example, you're going to have 50 pairs of sums that add up to 101, or 50 times 101. And since I went from 1 to 100 in that example, n in that example for me was 100. So this, for example, is n over 2 because you're creating a pair of numbers, right? So you're cutting your number of numbers in half. And then this would be n plus 1. And so this isn't necessarily the proof. I would have to use mathematical induction to prove that this is the sum. This is just showing you a numerical example of how that sum came to be. So this is the sum of all I squared. So for example, 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way up to, in this case, n squared. And this is what you get if you add them all up, depending on what n is. And then the last one is adding up all the sum of all the cubes. And then your sum would be n squared times the quantity n plus 1 squared all over 4. So let's just work with the basic idea of sigma notation, right? So writing this summation out. So if this is what I'm adding every time, I'm first of all going to be adding a finite amount because I can see that the dot, dot, dot in the middle right here shows that there's some in between here, but I see a last term. There's no dot, dot, dot on the end. What I can say is my numerator is 5 all of the time. If I'm looking for a pattern in each one of these fractions, I can see that the denominator is 1 plus all the time. That does not ever change. But then what does change is this number after it. So if I call this I, for example, that would then be my first, my second, my third, my fourth, all the way to my 15th. So I'll say this is 1 plus I. I'm going to sum all of these up, starting at I equals 1, and not just going to n, because again, this isn't an unknown amount. I'm going to stop at I equals 15. And so that would be my sigma notation to represent that sum. And we're going to need this as we go through and develop the idea of Riemann sum here throughout the chapter. So let's look at this one. Use properties of summation to evaluate the sum. So now I'm giving you a summation and you're going to have to figure out what that sum is. So I did distribute that I, so that I times I squared is I cubed and I times 1 is I. So I'm really looking at the sum from 1 to 10 of all I cubed plus I. And one thing to note about sums is it's very similar to our limits in that if I have a sum of a sum, okay, a summation of a sum, then I can rewrite this and say that this is the sum from 1 to 10 of all I cubes plus the sum from 1 to 10 of all i's. And I can copy these down and from above. So the sum of all I cubes, for example, I'm just going to put it down with the n's first. That is n squared times n plus 1, that quantity squared, all over 4. And then the sum of all i's, which we kind of developed together, is n times the quantity n plus 1, all over 2. And then n in our example here is 10. So I plug 10 in, which I did. So once you plug the 10 in, you're going to get 3,025 plus 55, or a total of 3,080. Okay, and again, we're going to use this idea of summation notation once we develop the Riemann sum. Okay, so now let's look at a problem where we're going to have to get a graph of something, and we're going to have to approximate an area. So we're going to estimate the area under the graph of f of x equals square root of x from x equals 0 to x equals 4. And we're going to do this using 4 approximating rectangles. And we're going to do this first with right endpoints. We're going to sketch the graph and the rectangles, and then we're going to answer the question, is your estimate underestimate or overestimate? And then we'll do the whole thing again using left endpoint. So we're going to get a good graph first of our function. And again, we're working with the function f of x equals square root of x. We're only looking from x equals 0 to x equals 4, and so we're going to get a good graph of that. So I graphed y equals square root of x. Again, I'm trying to draw underneath of it, so I maybe exaggerated this a little bit, or just think of this as a really zoomed in graph of my function, because 1, for example, is way up here. Okay, so the first thing they ask you to do is we're going to estimate the area under this curve, and we're going to do this using rectangles. And it tells us using 4 approximating rectangles. These rectangles are certainly approximating because they're used to estimate the area of something that is curved, and a rectangle certainly is not curved. And first it's asking me to do right endpoints. So I need to know how to draw these rectangles and how wide to make all of these rectangles. And it is important to note that if you're putting in 4 approximating rectangles, you want all the rectangles to have the same width. So let's just think about this for a minute. If I'm going from x equals 0 to x equals 4, and I'm putting in 4 rectangles, as you see here, each rectangle has a width of 1. Well, there's actually a formula that tells me this. Since my rectangle is sort of standing up, and I'm calling this base here, or what's on the x-axis, to be the width, we actually are going to call that delta x, or change in x. So what I'm going to say is delta x is actually my end, or my b, minus my start, or my a, all over n. So let me show you numerically and see if this makes sense. I end at 4, I'm starting at x equals 0, and I want to put in 4 of them. 4 minus 0 divided by 4 is 1, which tells me all of my rectangles have a width of 1, or delta x is 1. Okay, so now that we have our delta x, we're going to draw each rectangle. And we're going to do the right endpoints first, which I've tried to highlight in green, and I'm going to try to draw those again with you so that this hopefully makes sense. So every rectangle has a width of 1. So I'm going to start with that, the width of 1. And I draw the base of that rectangle on that x-axis there. And the right endpoint says that you're going to carry up the right edge of that width. And wherever that meets your curve, that is the height of that rectangle. So that rectangle has a height of 1. Now, each rectangle's area is very easy to figure out because the area of a rectangle, right, area of a rectangle is just base times height or length times width, however you want to think about it. So I've already got the width is 1, and now my height was 1. Well, if my width is always 1, I don't necessarily need to say 1 times the height plus 1 times the height plus 1 times the height. Instead, I can factor out that delta x. In this case, it's a 1. And then I can just add up all of these heights because, again, all of my rectangles have the same width. So it's 1 times the height plus 1 times the height, right? You're adding each area of each rectangle together. So now my next area of the rectangle, again, it has a base of 1. So it's going from x equals 1 to x equals 2. And I'm going to do the right endpoint. So I'm carrying up the right-hand side of it, and that will determine the height of that rectangle. And that rectangle has a height of square root of 2. And then my third rectangle, maybe by now you're seeing it, I'm not sure, goes from 2 to 3. And so then if you follow up that right edge, because again, we're using right endpoints, that right edge determines the height of that rectangle, and that one would be square root of 3. And then my last rectangle, again, because it said to put in 4 of them, and I already have 3 heights there, so the very last rectangle will be from 3 to 4, so the right edge has a height of 2. And so if I put this in my graphing calculator, I can get an estimate, because oftentimes they want an estimate or an approximation accurate to so many decimals, but certainly we could leave it exact and just say 3 plus square root of 2 plus square root of 3, but we can also figure out that decimal. So it's approximately 6.146. So that's what I'll say. Okay, now how can I tell if this is an underestimate or overestimate? Well, since we have our graph here, we can see that it's going to be an overestimate, because if you look at the green rectangles, I'm calculating, for example, all of that area that I just shaded in green that's not necessarily under my curve. I have extra area that I'm calculating here in my approximation. So I know that this is going to be an overestimate. All right, let's do the same thing now, but with the left endpoints. So my width, it's important that you know, it's still staying 0 to 1. So my width is going from 0 to 1, but now I'm going to use the left endpoint as the height. And my left endpoint is down here at 0, 0. So all of my rectangles are still 1 wide because I'm not changing the width of them. This one still, for example, is going from 0 to 1, but in this case, the left endpoint has a height at 0. So my first rectangle is right here from 0 to 1. It's actually just a flat line, has a height of 0. The second rectangle is going from 1 to 2, so again, still having that width of 1, but you're following the left edge up. And this is the rectangle that you have for rectangle 2 for your left endpoint, so that has a height of 1. My third rectangle will go from 2 to 3 on the x-axis, but you follow up the x equals 2 because that's your left side. That will determine the height of that rectangle. And so that height would be square root of 2. And then your last rectangle, using left endpoints, is going from x equals 3 to x equals 4. Carry up that left edge, which is x equals 3. And so I have a height of square root of 3. And so this one should be 2 less than that one. So even if I use my calculator, I should get approximately 4.146. And just by looking at my rectangles, I can see that these pink rectangles that I drew here are going to be underestimates. They're not going to be enough to actually calculate my total area under my curve, because I have area that I haven't even added yet. For example, all this area that I just put in blue, I didn't account for that area at all. This area right in there, the area right in there. Each rectangle is an underestimate, so the whole thing is going to be a little bit too small. So we actually did everything in the problem. Let's reread it and make sure so you understand what we did. Estimate the area under the graph of f of x equals square root of x, and then it's going to tell us how to do that. From x equals 0 to x equals 4, so we drew it. Label your points using 4 approximating rectangles. This delta x told us how far our x's needed to be separated out. Sketch the graph and the rectangles. We did that. Is your estimate an underestimate or overestimate? And then repeat using the left endpoints. So we have done all of that. So it's also important to note that your answer should make sense. So if you have two answers of 4.146 and 6.146, it should make sense to you that the smaller area represents your underestimate and your larger area should represent your overestimate. So let's look at another example, one that gives you information in a little different way. This question says, the speed of a runner increased steadily during the first 3 seconds of a race. Her speed at half-second intervals is given in the table. Find lower and upper estimates for the distance she traveled during those 3 seconds. Include proper units in your answer. So now this is actually going to mean something. And I left the answers here only for computational sake because I don't think we need to take video time to type things into our calculators. First things first, if I envision this problem as a function, my time in seconds would be my input, and my velocity or speed in feet per second is going to be the height of my function. So if I just think back to area of a rectangle, and I think back to it's just good old base times height, let's do this using our labels and make sure that our labels make sense. So my base, or my x-axis, if you will, is going to be in seconds as a unit or label, times my height, which is my height of my curve or the height of my rectangle at any given point, which is now going to be in feet per second. Because you want to make sure that if you're finding the area of your rectangles and adding them all up, that your units or labels make sense as well, because sometimes we don't measure things in the same way. I'll show you what I mean in a few minutes here. So seconds divided by seconds is 1, or that ratio would be 1, and I am left with feet. So if I find the area of these rectangles and I add them up, I'm actually figuring out how many feet did this runner run. So for example, my underestimate is 34.7 feet and my overestimate is 44.8 feet. And you should be able to tell that just from the two answers. So if you're given a table, I don't necessarily recommend that you draw it. You don't have a function to put in your y equals. All of the values are already here that you need. So let's think about this. If you calculated every half second the runner's speed, every half second then you have a y value that you took. And this is good data usage as well. If you take data every half second, your hope or your intent would be then to use the data that you took every half second, or why did you bother taking that data? So when we're making these calculations and using our data, not just a function, right, but using a table like this, we want to make sure we use as much of that data as possible. I want then delta x to be 0.5. In other words, I want, if I think of this as an x-axis, I want the first rectangle's base to be from 0 to 0.5, and I want the second rectangle's base to be from 0.5 to 1. And then depending on if you're using left endpoints or right endpoints would just depend on which one you're using. If you needed to know, you could figure out how many rectangles you're putting in, because you could use your delta x formula sort of backwards, right? You know delta x is a half. You know you're ending at 3 and starting at 0. You can figure out how many rectangles you're putting in. So 1/2 equals 3 over n, so n must be 6. So I'm putting in 6 rectangles. So I'm going to need to find, for the upper and lower estimates here, I'm going to have to find 6 different heights. Okay, so let's start. If I'm looking at this little drawing here where this hand is, because again, I'm going to delete it here in a second. If I'm drawing a rectangle and the base goes from 0 to 0.5, I'm going to follow the left edge up, right? And that will determine my first height of my first rectangle. And so I'm going to talk about the area of the left first. They're all 1/2 wide. So all of the bases of every single rectangle should be 1/2. So again, you could do 1/2 times the height plus 1/2 times the height plus 1/2 times the height, or you can just factor out that 1/2. Now, if you're starting on the left, your first height is 0, your second height is 6.2. I'm sort of marking these on the table. Your third height would be 10.8, your fourth height would be 14.9, your fifth height would be 18.1, and your sixth and final height would be 19.4. And so I label those as L's. So I'm going to write 0 plus 6.2 plus 10.8 plus 14.9 plus 18.1 plus 19.4. And you multiply all of that out and we're going to get a number. All right, let's do area of the right. It doesn't matter if you're using left endpoints or right endpoints. I did not change the width of my rectangles. So in this case, each rectangle is still 1/2 wide, but now I'm starting on the right, and some people like to start literally on the right side of their data. The first height would be, or really the last height, depending on how you're reading this, would be 20.2. That's the first. And that should make sense to you because if your rectangle is going from x equals 0 to x equals 0.5, you're going to use the 0.5 height of 6.2 to determine the height of that rectangle. Again, you're welcome to draw this out if you think that's going to help you. So I add up these values: 6.2, 10.8, 14.9, 18.1, 19.4, and 20.2. Now, these do align, but let's talk about why. So if I know that my function is increasing, I could draw that, right? It increased steadily. So if that's the case, and think about these rectangles. So just think about a rectangle from that x value to that x value. You could just pick out 2 x values. If you use left endpoints, you're going to be below. So left in this case would be my lower estimate or underestimate. But if you take your right is going to be bigger, or the right is your upper estimate. And that will be true if you increase the whole time. So I knew because I increased that my right should be my overestimate and my left should be my underestimate. But again, you can tell based on the numbers which one is your under and which one is your over as well. And then lastly, don't forget to label feet. Because that's what we came up with at the very beginning of the problem. Okay, one more here, and then we'll get to something else. So the velocity graph of a braking car is shown. Use it to estimate the distance traveled by the car while the brakes are applied. Be sure to include proper units in your answer. So again, we're going to use rectangles, but it just says estimate the distance traveled. So we're going to have to figure out what would be the best estimate. And so hopefully what you can see from the previous table or from our previous graphs that we did in this problem down here, that the lower or left or right rectangle approximations are not going to always be the best. But let me pose a different scenario here. What if I kept the width of this rectangle as 1, but what if I used the midpoint between 0 and 1 just to determine the height of that rectangle? So if we use the midpoint to determine the height, again, I'm not changing the width or the delta x at all, what you'll notice is I have a little bit less of extra area, but I also have some not enough or too small of area that I did not calculate and should have. And so what we actually find is that that midpoint, and in each scenario here, I can follow up the midpoint and I can use that to determine the height of the rectangle, and that's going to be a better approximation than left or right alone in most cases. So that's what we'll look at on our braking car graph. So since we want that best estimate, we're going to look at creating rectangles and then trying to find the midpoint. And it really is up to you how many rectangles you use, because they're not telling you, they're just saying get a good estimate, right? Try to figure out the distance traveled by the car. So again, try to use as much information from the graph as is shown. So if I'm going from 0 to 6, it might make sense to me to just use 6 rectangles, and that would be fine. If you're finding these graphs hard to read, because for example, if you're going to put in 6 rectangles, your rectangle widths are 1, and so if we're going to use midpoints, we're just going to follow about halfway through up, and we're going to estimate what that y value is. Delta x is 6 minus 0 over 6, again from a to b, so b minus a, where do we end, where do we start? So 6 minus 0 all over 6, so I want my delta x to be 1. So my area, and again, I'm using mid. I just tell myself it's not a left, it's not a right, it's a midpoint approximation. All of the widths are still going to be 1. However, the height of the rectangle is now determined by the midpoint. So this one looks, I don't know, about here. And what's even harder is each of these y increments is 20. So maybe that's 54. I don't know, you're going to kind of estimate here as you wish. The second rectangle is going to be from x equals 1 to x equals 2, right? 1 wide. So the midpoint, so go about halfway. Ooh, that one's nice, about 40. All right, my third is going to go from 2 to 3. Follow up that midpoint as best you can. So 30, not quite. We'll say 28. Again, if you said 30, that's fine. There is a tolerance built into all of these. So then from x equals 3 to x equals 4, 18 maybe, I don't know. And then let's go from 4 to 5, about the midpoint. Maybe that's halfway up, so we'll say it's close to 10. And then from 5 to 6 finally. Got to be less than 10, so we're going to say 6. I don't know. And then we're going to add all this up. All right, 156. And before you go on, let's make sure we use proper units in our answer. So think about just one of these rectangles. Well, the base or the width of that rectangle is in seconds, and the height is again in feet per second. So absolutely, my area label or unit makes sense in this case. This tells me I've traveled approximately 156 feet. And please make sure that it makes sense. We are in a braking car for 6 seconds. It does not make sense that we go, for example, 156 miles, right? We're only traveling for 6 seconds, and we were traveling, sure, I mean, decently fast at first, right? But again, these are feet per second, not mile per hour, and we are braking, so we are not accelerating, and we're only traveling for 6 seconds. So going 156 miles, for example, would be pretty aggressive. We typically measure these things in miles per hour, and we talk about how many seconds it takes that car to brake. So here's my braking car. All right, so if I go now to just finding the area, and numerically that should be, relatively easy for us to do using those summation rectangles. I'm saying that they're all wide by how many seconds, right? So let's say this is one rectangle, but the height is in miles per hour. So what might happen is, let's say again that this is 6 seconds, and if I started going at 60 miles an hour, then yes, maybe I could have gotten something like 156 miles as my answer. That doesn't make sense. Second miles per hour isn't something that would signify to you, oh, that's how far I traveled. So we do have to do a conversion here. Now, this is something that we often do is we often measure our speed in the United States in miles per hour, and we time things on how many seconds it takes. So how fast can your car accelerate is usually measured in seconds. Say, how fast can your car get to 60 miles an hour in how many seconds? We don't talk about that in terms of how many hours did it take. Let's convert here. So I'm going to say 1 hour is equivalent to 60 minutes. So that's really a ratio that represents 1. And then I'm going to say 1 minute is equivalent to 60 seconds because, again, now that's a ratio that is really equivalent to 1. So minutes over minutes, seconds over seconds, hours over hours. So I really have whatever my numerical answer is, and I'm going to have to divide it by 3,600. Then I will know how many miles I have traveled. So you might underestimate how important your labels really are when you're looking at these problems. And it's easy to just get caught up in finding the area using the rectangles because we usually like rectangles. It's an easy area to find and add them all up. So we like that. However, just pay very, very close attention, please, to your labels or units. Thanks for watching.